Okay, a couple of announcements here. So our second test, which was originally scheduled for next week, is now going to be moved to the week after spring break. This is being done for two reasons. One, we were already a little bit behind before the snow day today, and now we're even further behind an entire week. And also because I now cannot give back to you your past homework assignments that you would presumably need to study from. So I'm going to be moving the test to after spring break. And also I've placed a homework assignment up on Blackboard. This is an assignment that you'll actually complete online and submit. It's rather quick, rather simple, to go along with this rather quick PowerPoint presentation for tonight's lecture. So the topic of today's lecture is gamma ray bursts. And gamma ray bursts are interesting because they were discovered accidentally back in the 1960s. And I want to get into how they were discovered. And to do that, we have to start at the end of the Second World War, at a time that the United States and the Soviet Union entered into what we call a Cold War. It's called a Cold War because it's a war that didn't have any violent confrontations. But there was a lot of tension, and the people in both countries and the rest of the world kind of had to live under constant threat that something could happen. And something major, because both countries, and to a lesser extent Great Britain, were embarked in a huge, massive arms race where stronger and stronger, more powerful nuclear weapons were being devised as the years passed. And this culminated with the largest explosion ever produced by mankind on the planet, and it was nicknamed Tsar Bomba. I show here a couple images of Tsar Bomba. Tsar Bomba was a 50 megaton nuclear bomb. Pictured here on the left, this is the actual fireball created. It was 8 kilometers in diameter and nearly took out the plane that dropped the bomb itself. Over here on the right, you see a picture of the resulting mushroom cloud. This bomb was detonated here in Siberia, northern Russia. And you can see here this plot showing you how over the years the size of these bombs, or the TNT equivalent for these bombs, actually increased with time. You can see Tsar Bomba here at 50 megatons. You can see down here we got 10 and 15 megaton bombs in the United States. And in this teeny little circle here we have Hiroshima. And everybody here has seen images of the devastation leveled on Hiroshima, Japan with this bomb. So you can imagine the damage in a populated area by Tsar Bomba. So from the late 1940s to the early 1960s, the United States and the Soviet Union were regularly conducting nuclear testing, testing ever more devastating nuclear weapons. In 1959, radioactive deposits were found in samples of wheat and milk in the northern United States. And the reason this was happening is most of the nuclear testing in the United States was done in Nevada, at the Nevada nuclear test site. Well, when these nuclear weapons were detonated, radioactive material will be thrown up into the atmosphere. That radioactive material would ultimately make its way back to the ground and result in nuclear fallout being distributed in low doses all over the United States. So when these deposits were discovered, there was a general outcry from scientists and the general public to end nuclear testing. Because we're ingesting this material as Americans. Radioactive material, when it decays, gives off high energy photons, high particles that can do damage to tissue. And so this was having a noticeable impact. The plot that I show here is from the National Cancer Institute, and it shows the equivalent radiation exposure due to the nuclear testing period back in the middle of the 20th century. What you can see is for the heaviest states, the states with the most radiation exposure, they were exposed the equivalent of 12 to 16 rad. And to give you some idea of that scale, a normal exposure, this is just due to naturally occurring radioactive species, is about 0.1 rad per year. So the nuclear testing was actually having a considerable impact over what the average would be in a normal situation. If you get a single chest X-ray, you're exposed to 0.007 rad. If you get exposed to more than 1,000 rad in a short amount of time, you're most likely to die. It's invariably fatal. So these are rather low doses, but yet could still have potential health effects on people nonetheless. So there was this general outcry for an end to nuclear testing. So this general outcry ultimately led to talks being initiated between the United States and the Soviet Union that would ultimately lead to a testing ban. Okay, early talks were stymied by disagreements between how you would enforce a nuclear test ban. The United States wanted to engage in inspections, and the Russians, or the Soviets feared that it would lead to spying naturally, so the talks halted. Then came the Cuban Missile Crisis. And history teachers could teach an entire semester on the Cuban Missile Crisis. So I'm not even going to try to get into any detail on it, but I just want to say that basically what was happening here is you had the Soviet Union trying to place nuclear missiles in Cuba. The United States, of course, wasn't too happy about this because that put them in easy striking distance of every major U.S. city. And so the United States engaged in a blockade, and the blockade is pictured here on the map. This brought the Soviet and American militaries in close contact to one another, and in fact, one American boat was actually destroyed, so there was actually a missile fired, or excuse me, not a missile, but there was actually a violent confrontation, and so both countries were very close to being on the edge of nuclear war. And so ultimately, it was resolved, thankfully, but it scared both the Soviet public and the American public to such an extent that both Kennedy and Nikita Khrushchev, who are pictured here, decided to reopen talks, partially as a means to calm down the general populace in their countries. So in 1963, the United States, the Soviet Union, and Great Britain signed and ratified what's called the Partial Nuclear Test Ban Treaty. Okay, this treaty was designed to end all nuclear testing on land, in the water, and in the atmosphere. Okay, this was so what was still allowed was the testing of nuclear weapons underground, and that sort of testing went on for during the years afterwards. But all testing on the land, in the water, and in the atmosphere was banned. This is a picture of Kennedy actually signing the Partial Nuclear Test Ban Treaty. So what does this have to do with gamma ray bursts? Okay, the astronomical object we're interested in here are gamma ray bursts. Well, in October of 1963, the United States Air Force launched a series of satellites whose main purpose it was to enforce the Partial Nuclear Test Ban Treaty. It was a set of satellites whose goal was to detect nuclear explosions in the atmosphere or on the ground around the globe. Okay, the satellites were called the Vela satellites, and this was derived from the Spanish word velador, which means the watchman. And these satellites were equipped with X-ray, gamma ray, and neutron detectors. Okay, all three of these things, X-rays, gamma rays, and neutrons, are created in a nuclear explosion. Okay, so these things were positioned around the globe in orbit around the Earth, and they were searching for violators of the Partial Nuclear Test Ban Treaty. So the Vela satellites were up there, and they were monitoring the globe for nuclear explosions. Okay, they were looking for sources of gamma rays, X-rays, and neutrons. So they made detections, and not all detections were realized to actually be nuclear testing. And in 1965, the powers that be, I've written up here on the slide, this was the researchers at the Los Alamos National Laboratory, began to file away the data on these false detections, or quote-unquote false detections, for future study, just in case that they were something interesting. In 1972, astronomers finally actually took the time to look at this data, and what they found was that what they were seeing were incredibly bright sources of gamma radiation. They were irregular, and they lasted only a few seconds in time. So these sources of gamma radiation were dubbed gamma ray bursts because they were short bursts of high-intensity gamma radiation, gamma ray bursts, or GRBs. They were ultimately they were ultimately resolved. The positions of these objects were ultimately resolved in the sky, and it was quickly realized that they did not come from the Earth or the Sun. They didn't have a terrestrial source, and they didn't have a solar source. So they were coming from some source outside of our solar system. This is the actual paper which announced that. This was in 1973. And the last section here says directional information eliminates the Earth and the Sun as sources. So we knew these things were coming from outside of our solar system, and at the time that was described as having a cosmic origin. Okay. Now, between this 1973 paper and the early 1990s, we didn't really know what these objects were, these gamma ray bursts. It was guessed, it was assumed that they were some form of scaled up X-ray burster. If you remember the X-ray bursters, this is when you have a neutron star orbiting a companion star, and when the neutron star starts gobbling matter from the companion star, it can give off high intensity radiation in the form of X-rays along jets. Okay, we have these X-ray bursters. And what we were seeing in these gamma ray bursts were much more energetic, but we figured they were just, as I say here, scaled up X-ray bursters. We now know this is not the case. So in 1991, NASA launched the Compton Gamma Ray Observatory, CGRO. And this observatory's aim, this was a space telescope, its purpose was to observe the universe in gamma rays. Okay, we've talked about the electromagnetic spectrum, and you guys should know now that gamma rays are the most energetic form of electromagnetic radiation. These are very high energy radiation. And we've talked about how the universe looks different in the different wavelengths of light. Okay, you can learn different things about an astronomical object by observing it at different wavelengths. The CGRO, its purpose was to observe the universe in gamma rays. And one of the things that it informed on more than anything else were gamma ray bursts, because these were astronomical objects that emitted most radiation in gamma rays. Okay, so you can see I have here the Compton Gamma Ray Observatory pictured here on the left, and here we have the electromagnetic spectrum showing you all the different windows of radiation, going from the high wavelength radio waves to the very low wavelength high energy gamma rays. So the CGRO operated for about 9 years, and it detected over 2,700 gamma ray bursts during its operation. This averaged to about 1 gamma ray burst per day on average. You can see 3 examples here. These are 3 gamma ray bursts that went off in 1991, and you can see that they vary widely. Some of them this first one here lasted for 5 seconds, and it had a bunch of pulses, peaks and jumps. Here's one that was emitting radiation over a period of 80 seconds, giving once again some erratic peaks of bursts of energy. And then you have this last one here, May 18th, 1991, this one was a very, very short period gamma ray burst. So these things have a wide variation in the light curves that we actually see for these gamma ray bursts. And this wide variation may suggest that there are multiple physical mechanisms that actually bring them about. And we'll talk more about that here in a minute. So as we said, the paper in 1973 from the researchers at Los Alamos said that the source of gamma ray bursts was outside of our solar system. So does that mean that the sources are galaxy sources, galactic sources? Like, for instance, the X-ray bursters theory? The X-ray bursters are basically a stellar source. These are stars. So if we looked at, for instance, the night sky, we should expect to see more of these things at locations where you get clumps of stars, right? That would stand to reason. If these are stellar sources, we should see more of them where there are lots of stars. Well, if you take a look at a 360-degree panorama of the sky, this is what you see. You see this band that goes across the sky, 360 degrees, that represents the Milky Way. This is the disk of our galaxy. This is when we look along the disk of our galaxy, we see lots more stars. And we see very few stars up here. So if a gamma ray burst was a stellar source located within our galaxy, we would expect to see concentrations along the Milky Way. This is what we actually see. We actually see a pretty uniform distribution across the entire sky. We don't see any heightened concentrations in the disk of our galaxy. This is pretty strong evidence that gamma ray bursts are from sources outside of our galaxy. So gamma ray bursts can be a tricky object to observe because they are so short-lived. These things, even the long ones, have bursts that last only tens of seconds. So what we'd like to be able to do is measure this thing in multiple wavelengths. Most of the energy comes off in gamma rays, so they're often detected in the gamma rays. By the time the burst is over, it's so faint that we can't observe it at other wavelengths. This ended in 1997 when there was a gamma ray went off, 971214, that was imaged simultaneously. Well, not simultaneously, but in rapid succession in gamma rays, X-rays, and the optical. Okay, this is the code for gamma ray bursts, 971214. 97 is the year that it was discovered, 12 is the month, and 14 is the day. So this particular one was discovered on December 14th, 1997. This one showed what we call optical afterglow. It's emission by the gamma ray burst in the optical. And what it allows us to do is oftentimes you can get a spectrum of the optical afterglow, or in the case of 971214, several weeks later you can take a look at it with HST and you can actually make out the host galaxy, which is pictured here, of this particular gamma ray burst, and take a spectrum of it. When you take a spectrum of it, what you find is spectral lines that don't match spectral lines you know of in the laboratory. You can recognize the patterns, but the lines appear to be shifted, and we've talked about this already. This means that these lines have been redshifted. And what this means is that these galaxies are actually moving in the radial direction relative to the Earth. And these ones were redshifted by so much that it implies that they lie very, very far away from us. In fact, the redshifts of almost every gamma ray burst imply that they reside billions of light years away from us. Okay, so we're looking across large expanses of the observable universe. The diameter of the Milky Way itself is only 30,000 parsecs, and yet this particular one, this is gamma ray burst 970508, was shown to be 2 billion parsecs away from Earth. Okay, so these things, gamma ray bursts, not only are not in our system, they're also not in our galaxy, and they're some of the most distant things that we observe. So at this point, more than 200 optical and X-ray afterglows have been detected, and the distance to several dozen gamma ray bursts have been determined. And so we know the gamma ray bursts are quite distant, as I just pointed out. The interesting thing is they are very bright. Okay, and we're able to see them in spite of the fact that they're so far away. Now remember, the inverse square law says the intensity of light falls off as 1 over r squared. So when you double the distance to a source, you're going to decrease the intensity of that light source by a factor of 2 squared, or 4. So the intensity of light falls off pretty quickly. So these things are incredibly far away, and yet we're still able to see them as bright sources. This means that the amount of energy that they must be giving off is tremendous. They are basically producing, at times, hundreds of times the energy of a supernova explosion, but they're doing it in a matter of seconds, whereas a supernova does it over the course of a couple hundred days. So this is a tremendously huge source of energy, and it certainly raised red flags in astronomers' mind, which is why I have here, because it seems there's something inconsistent here. Something this tremendously energetic doesn't seem likely. In fact, gamma ray burst 971214 that I pictured is considered, at the time it was considered, the most violent explosion ever observed in the universe. Based on its distance and based on its brightness here, you can extrapolate backwards and say what its total energy output would be. and it was violent explosion ever observed in the universe. But what are they? Okay, what are they and what else do we know about them? Well, first of all, we know that they have really quick changes in their brightness. Okay, you get these pulses over very, very short times, okay, milliseconds even. So one thing we know about is if a bright source changes its brightness over a very short amount of time, whatever's causing this bright object has to be very small. Okay, and to understand this, I'm putting up this example here. Say we have some astronomical object, okay, that has an extent of about 1 light year. Okay, so it's a rather large object. And it has a certain average brightness. Okay, if its brightness changes, let's see what would happen. Well, its brightness would click on, and the light from the front of that object would start, the brightened photon, the heightened light, would start traveling towards the Earth. And it would travel towards the Earth at the speed of light. Okay? At the exact same time, light from the back side of that object would also proceed towards the Earth at the speed of light. Now what does this mean? It means that up until that first photon arrives, we still see it as the duller, fainter object. And it's not till the extra photons come to us from the front of the object that we start to see it brighten. So it's going to slowly begin to brighten. And it's not going to fully show us its full brightness until the last photons arrive, which are going to arrive 1 light year later. So what we're going to see on the Earth is not an instantaneous brightening of this thing. We're going to see a gradual brightening over the course of 1 year for this particular object. This tells us that this object is about 1 light year in size. So in general, you can pretty much state that an object can't flicker unless it takes radiation, light, to actually cross that object. Okay? So what does this mean for gamma ray bursts? Well, gamma ray bursts vary over milliseconds. This means that whatever is causing the gamma ray burst, the source of this emission, it can't be more than 1 light millisecond in size, the length that light travels in 1 millisecond. So this is roughly about a size of 300 kilometers. Okay, so whatever the physical mechanism is, it has to be pretty small, smaller than 300 kilometers. There are primarily 2 theories involved in the origin of gamma ray bursts, and they're called the merging stars theory and the hypernova theory. Okay, and both of these theories involve what we call a relativistic fireball. A fireball is created, okay, that creates high energy particles that are traveling close to the speed of light. They're emitting most of their radiation in the gamma ray part of the spectrum, and that gamma radiation is emitted towards the Earth. So this radiation comes off in jets. Okay, we've talked about jets in the past, jets of hot gas that are moving at the speed of light. And one of the things that this does is it kind of explains away these ridiculously high energies that we've attributed to these events. And to explain that, let's take a look at this. What I pictured here is I pictured some object, okay, some explosive object that's sending its light to the Earth. Okay, when we look at how much energy actually makes it to us from that object, we could assume, the natural thing to assume is that it's a spherical explosion, it's a spherical event, that it's not just preferentially sending out its radiation in our direction, that if this is the energy that we're seeing, it's also getting that same amount of energy in all directions. Okay, so when we're summing up how much total energy is released, we have to sum it up over a 3-dimensional sphere. This means that we would interpret it as lots and lots of energy, and that's what we've done. However, if it's like a gamma ray burst, and the model is more accurate to say that it's caused by jets, then the energy that we receive is not being emitted in all directions. It's actually only being emitted along 2 cones. And we just happen to be in the crosshairs of this particular gamma ray burst. So what would result here is if we were to integrate all of the energy being emitted, we're not going to integrate it over the entire sphere here, it's just going to be over these two jets. So this would result in a prediction of much less energy actually being emitted by these gamma ray bursts. Okay, so these ridiculously high energies of several hundreds of times the energy of a supernova explosion emitted in a very short time are removed. We don't have to worry about them. These ridiculous amount of energies that would be predicted are solved by the assumption that this is a system involving a jet. And the variability that we see in the light curves has to do with what the line of sight we see for the jet. If we're looking directly down the beam, if we're looking slightly off to the side, etc., it could have a major impact on what we actually see. So these are the two theories. Okay, the first theory that we were calling merging stars basically involves the merger of two neutron stars. Okay, we've talked about how the brightest supernovae are the type 1a supernovae, and they are the result of the merger of two white dwarf stars. The gamma ray burst, is argued, could be caused by the merger of two neutron stars. When these two neutron stars come together, they form a high temperature accretion disk. The energies that are emitted in the center are going to be funneled along the poles and create this relativistic fireball that we talked about. We could also have the hypernova scenario. The hypernova says we just have an incredibly massive star, so incredibly massive that neutron degeneracy cannot halt the collapse of the core, and so a black hole is formed, and we're going to be moving on next week to our discussion on black holes. This black hole actually stalls the supernova explosion. It has such a tremendous amount of gravitational pull that shock wave is stalled as it tries to leave the star, and it results in a accretion disk forming around the black hole. Once again, we get a relativistic outflow moving along the poles, and we get this jet of material. If the Earth happens to be in line of this jet, we would see a gamma ray burst. So these are the two main models, the two main theories behind the origin of gamma ray bursts. And these things are still being studied today. So this isn't something that's already solved and we're moving on. This is hotly debated, hotly discussed, even today. So the prevailing theory here is that the long gamma ray bursts, these are the ones that last more than 2 seconds, these are caused by the hypernova scenario, and that the short gamma ray bursts are the ones that are occurring over the merging neutron stars. Okay, so these are the two theories of gamma ray bursts, and this is the end of our discussion here on gamma ray bursts in section 4. So I want to make sure that you go ahead and you read the chapter or the section on gamma ray bursts, and you should now go to Blackboard under course documents and find homework 9. Homework 9 is a series of questions on the material covered in this lecture and covered in the textbook. Okay, it's rather quick, but I wanted to give you guys something to continue to your thought about astronomy over the course of this week, since we didn't get a chance to meet thanks to Mother Nature. Okay, so complete this assignment online. It will automatically record your result. I'll grade the essay parts of the test, and then I'll see everybody next week. So remember that our exam, our second test, is not going to be until the week after spring break. Okay, so I'll see everybody next Wednesday.